Welcome everyone to phase 7. We're going to be looking at trigonometry this chapter. So getting right into it, because there's a lot to get through this chapter, we're going to be looking at what's called special right triangles. And special right triangles are triangles that are made up of 45, 45, and 90 degree angles, or 30, 60, 90 degree angles. So you can see I labeled one of the 45s. If we know that's 45 and that's 90, the other one also has to be 45. Similarly here, if this is 60 and that's 90, that also has to be 30 down here. So these are all 30, 60, 90s, and these are 45, 45, 90s. So those are what are called special right triangles. Just because those numbers are special in consideration to the number 90, right angles, right? These are half, and this is a third and 2/3 of that number. So those are kind of the nice triangles when it comes to right triangles. And they have some special properties. So on 45, 45, 90s, those make isosceles triangles, right? Two same angles mean two same sides. And what we can do is to use the Pythagorean theorem to find the hypotenuse of each of these. So go ahead and pause the video and see if you can work that out over the next couple minutes. The Pythagorean theorem for each one of these. And if you can, try to do the exact length. I'll explain what that means more here in just a minute. All right, let's see how far you've gotten so far. So setting it up, the legs squared have to equal the hypotenuse squared, right? 2 squared plus 2 squared has to equal this side squared. So that's kind of the way I set it up. And then I went ahead and did 2 times 2 is 4, plus 2 times 2 is 4 is 8. And then you square root both sides so that you get just the hypotenuse there. So the square root of 8 would be that side. Well, that square root of 8 can actually be simplified. If you take the number 8 and break it down into its factors, there's actually a perfect square, 4, that's baked inside of 8. When I say perfect square, I mean it's a number that you can get by timesing or multiplying something by itself, right? 4 is 2 times 2. So we can square root that part of the 8, get just a 2, and leave this extra part under. This is what's called simplifying square roots. You should have went over that in Algebra 1, maybe even 8th grade too. And similarly, I did the same thing down here. 5 squared plus 5 squared gives you a total of 50. And then if you square root both sides, you get the square root of 50 as our hypotenuse. That's what I mean by the exact length, by the way. I could take the square root of 8 in a calculator and get the decimal approximation, but that's a decimal that goes on forever. So we would have to round if we're going to write the decimal down. If you want the exact answer, you have to either type in 2 square root 2 or square root 8. See how that's the same number? This is just considered simplified because we found the perfect square inside of 8 and took it out. And the reason I wanted to do that, to simplify, is because we'll see a pattern emerge here. Hopefully it's a pretty obvious pattern you can see from just these first two. What we always get on this 45, 45, 90 is the leg. So no matter what the leg is, right? X can be any number. No matter what it is, this side will be the same as that side because it's isosceles. And the hypotenuse will be that number times the square root of 2. Again, this is a property that only, or a case that only happens on 45, 45, 90s. Not every right triangle does this. That's why they're considered special, is because they have a property like this. So this is a question that pops up on the SAT all the time, where you won't have enough time to sit there and work out a bunch of Pythagorean theorem stuff. But if you know that you have a 45, 45, 90, you can easily take that number and just tack the square root of 2 onto it, or multiply by the square root of 2 and get your hypotenuse. So there's a similar thing that's happening over here. Go ahead and pause and see if you can work these out. Just be mindful of the fact that you have the hypotenuse and a leg this time. So it's going to set up just a little bit differently. All right, so hopefully that wasn't terrible, right? Since we had the hypotenuse given to us this time, when you set it up, that hypotenuse has to go on its own side, right? And so when I set this up, I have an unknown leg squared plus the other leg squared equals the hypotenuse squared. So as I solve that, I would square both of these, 4 and 16, and then I would subtract the 4 away from 16, which is where I get 12. So leg squared would be 12. Square rooting that gives me the leg is the square root of 12, which again, I could type that in the calculator and get a decimal approximation for it, or I could see if I can simplify that. 12 breaks down into 4 and 3, and I can square root the 4 part. The 3 is the irrational. That's the part that gives us the infinite decimal. So we have to leave the 3 under the square root, and we can simplify the 4, square root of 4, just down to a 2. So the exact length of this side is 2 square root 3, or the square root of 12. It's the same thing. Similarly, down here, we get 100 minus 25 is 75, square root to get leg by itself. So this missing leg was the square root of 75. And once again, that breaks down into something that is a perfect square, so I can square root that part of it and just leave the other part under. And again, you see there's a pattern emerging here. We get the short side with a square root 3 on it. And also the hypotenuse, that's worth noting, is always going to be double the shorter side. So whenever we have a 30, 60, 90 special right triangle, the short side doubled. 2 times the short side, whatever that side is, will be your hypotenuse. And the longer leg will be the short side times square root 3. Again, this might seem a little trivial, just like, okay, like who cares? It's just a shortcut so you don't have to do Pythagorean theorem or what we're going to see later in the chapter, the trig ratios on every single problem. Sometimes these triangles that pop up a lot, they're shortcuts to be able to get to your answer. If you know one of the sides, you can figure the other ones out from it, which is what we're going to start doing down here. So if you're given a 45, 45, 90 or a 30, 60, 90, we can use just one side in order to find the other two. Right before, we needed at least 2 sides given to us in order to find the third side. But now that we know this ratio or this relationship, we can use just one side. So right off the bat, this is a 45, 45, 90. So I know that the 2 legs will be the same. So without even doing any work, I know this side has to be 20. Because it's an isosceles triangle, the legs have to be the same. And then I could jump in and do the Pythagorean theorem, or if I know this ratio from before, well, the legs times square root 2 is going to be the hypotenuse on any 45, 45, 90. So without doing any real arithmetic, I can jump right to the answer, 20 square root 2. And if I wanted to get a better idea of what that number was, I could just type in 20 square root 2. So that length is going to be about 28.3 right there. Again, this is irrational, so I would have to round it if I wanted to write like a number that my brain can kind of comprehend. The exact answer is 20 square root 2. All right, now that was the easy one, right? So here we actually have the hypotenuse, and we have to get the leg. Well, again, this would be really tricky to do without our relationships that we learned about up here. Well, we know that the 45, 45, 90's hypotenuse is just the leg times square root 2. So if I just divide off the square root of 2, that leaves me what the leg has to be, because it's the leg times square root 2 to get the hypotenuse. That's what we saw up here on the 45, 45, 90's. And if I know one leg, then I know both on a 45, 45, 90. So that's all there is to it. It gets a little trickier if the hypotenuse doesn't have a square root of 2 in it. So like if we have just we'd have just a hypotenuse of 10, well, you're still going to do the same thing of dividing by the square root of 2, but you don't actually want to do that division, again, because this is irrational. It gives you an infinite decimal, and you're not supposed to leave square roots in a denominator. I'm not actually sure why. It's just somebody decided, like, for the same reason that you don't leave 3/6 as an answer, you simplify it to 1/2. It's considered improper to leave a square root in a denominator. So whenever you have one, and again, hopefully you saw this in Algebra 1, you get rid of it by multiplying by that square root over itself. Something divided by itself is just 1, and multiplying by 1 doesn't change the problem. Sorry if that's really confusing if you didn't learn about it before, but it's a thing that we do. And when you do that, you have a square root times itself. So a square root squared just gives you that thing. A root being squared would cancel the square root out. And then up here, I would have 10 square root 2, which then I can simplify. 10 divided by 2 is 5 square root 2. Right? So that gets a little technical, a little tricky. 5 square root 2. And the same thing down here, both x and y would be 5 square root 2. All right, so let's look at the 30, 60, 90's. Well, remember the relationship here. The short side doubled is the hypotenuse, and the short side with a times square root 3 is the long side. The long side is the short times square root of 3. So if I know the short side, I can just double it to get the long side on a 30, 60, 90. And I just multiply it by the square root of 3 to get the long side. So short side times square root of 3 is the long side. Short side doubled is your hypotenuse, right? Really nice when you have a short side given to you like that. Well, when you have the hypotenuse given to you, it's still pretty easy. You just undo this step. Instead of multiplying to get the hypotenuse, now I'm just going to divide to get the short side. So if the hypotenuse is the short side doubled, then the short side is half the hypotenuse, right? Just reversing that logic. So 16 divided by 2 would be 8. And then to get the long side, I take the short side times the square root of 3. So 8 square root 3. And that's all there is to it. Well, once again, there is a bit of a trick when you have to go all the way back. If I have that long side and I want to get to the short side, right, to get short to long, I multiply by the square root of 3. So to get from long to short, I'm going to divide by the square root of 3. And you can see why that's going to be a bit of an issue here. 36 divided by the square root of 3. Well, again, I can't leave it like that, so I have to go square root of 3 over the square root of 3. That gives me a square root times itself, or a square root squared in the denominator, so I get just a 3. And up here, I get 36 square root 3. All right, you just put them together because they're being multiplied. And the 36 divided by 3 simplifies to 12 square root 3. So this is the length of the short side. And remember, to get from the short side to the hypotenuse, I just double it. So if I have 12 square root 3, the hypotenuse would be 24 square root 3. 12 times 2. Right, so it's just like taking this times 2. You don't double the square root. It's like if you had 3 times, let's say 4. 3 times 4, and I wanted to multiply that by 2. I don't multiply both. Sorry, if I had 3 times 4 and I want to multiply that stuff by 2, you don't distribute that in. You just multiply it with the stuff. So I'm just doing like this to get the 12 times 2 to get the 24 square root 3. All right, you've got a couple of consections, or I think maybe just one consection to practice on using this 30, 60, 90 relationship. So before we go on to the rest of the notes for this within this packet, go ahead and stop and go practice the con stuff for a little bit.